Hi, welcome to another session on Math for Data Sciences. So, in our last session, we started with applications of derivatives, and we saw that how we can use the differentiation of the any function to get their local maxima and local minima. So, what we observed was whenever there is a local maxima, the value of the slope of the function is positive behind the local maxima, and it is negative after the local maxima. And since the value of the slope, so value of the slope, which is the first derivative, is decreasing, therefore the second derivative has to be less than 0 for local maxima. And this was also the second derivative test to check whether a point is local maxima or a local minima. So in case of local maxima, the second derivative should be less than 0, and in case of local maxima, the local minima, the second derivative should be greater than 0. So we'll be quickly looking at one of the example here for a function which is fx equal to x raised to power 5 minus 2x cube plus x plus 2. So this is a 5-degree polynomial here, as the highest power of x in the function is 5. Now doing the first derivative test, we need to find the first derivative for the function. So for x raised to power 5, using the power law, we get 5x raised to power 4. Then x cube is 3x square, so minus 6x square. And for x, it's 1. And 2 is a constant, so it will be a 0. The first derivative will be 0. Now equating the first derivative to equal to 0 to get the x points of extrema, which is basically getting the critical points, what we do is we solve this equation. 5x4 minus 6x square plus 1 is equal to 0. Now let u is equal to x square. Then we are left with 5u square minus 6u plus 1 is equal to 0. This is a quadratic equation where it is of the form ax square plus bx plus c. Therefore, to solve this, we know that we need to use the quadratic formula. So we get u as equal to minus b. So it's minus b plus minus square root of b square minus 4ac upon 2a. So this is the quadratic formula to solve to get the roots of an equation of the form ax square plus bx plus c. Now putting the values from the above quadratic, we get u as equal to 6 plus minus 6 square is 36 minus 4ac. So 4 into 1 into 5, which is 20 upon 2a, which is 2 into 5, 10. This comes out to be 6 plus minus 36 minus 20 is 16, and the square root of 16 is 4. So we get 4 here upon 10. This comes out to be 1 or 1 by 5. Now that we have the value of u as equal to 1 or 1 by 5, we know that x square is equal to 1 or 1 by 5. Therefore, x equal to plus minus 1, because the square root of 1 is 1, or plus minus 1 upon square root of 5. So we have got the points of extremum now, but we still don't know whether out of these 4 points, that is plus minus 1 and plus minus 1 upon square root of 5, which one is a local maxima and which one is a local minima. So for that, what we do is we perform the second derivative test. So for that, we compute the second derivative. So the second derivative of fx is computed as the first derivative of f dash x, which is 5x4 minus 6x square plus 1. So 5x4 derivative is 20x cube, and then minus 6x cube minus 6x square becomes minus 12x. Now putting the value of any of these 4 points, so let's try it with 1. We get 20 minus 12, which is 8, and this is greater than 0. Therefore, plus 1 is a local minima. So if you remember, if the second derivative is greater than 0, as you can see from this particular chart, then we know that it is a point of local minima, and therefore at x equal to 1, we get a local minima as the value. Similarly, we can check for all the other points. So just checking it for minus 1 as well, let us say. So x cube, so minus 1 cube is minus 1, which becomes minus 20. Then minus 12 into minus 1 is plus 12. So this becomes minus 8, which is less than 0. Therefore, minus 1 is a local minima. So let us say right now we only want to check for these 2 points. So let us now try to find the values at these extrema. So f of 1. So we simply put the value of 1 in the function itself, and we get 1 minus 2 plus 1 plus 2, which is 2. Similarly, f of minus 1. So x raised to power 5 is minus 1. Then minus 2x cube becomes plus 2. And minus 1 plus 2. This is equal to 2 again. So we see that although the values here are equal, the point x equal to 1 is a local minima, and the point x equal to minus 1 is a, so minus 1 is a local minima, and minus 1 is a local maxima actually, because the second derivative was less than 0. So this is a local maxima, while plus 1 is a local minima. So how is that possible? So let us say if this is the graph, and let us say we have minus 1 here and plus 1 here. Now we have plus 1 local minima, so it is possible that the minima value is 2 here. So it is possible something like this, and the value is again local maxima in this case, while the value is 2, and local minima in this case, the value is still 2. So although the value of the function is equal at x equal to 1 and x equal to minus 1, the value plus 1 in this case is a local minima, while minus 1 is a local maxima, and this can happen in such a particular graph here. So this is how we can do the first and second derivative test for any function to find the local maxima and local minima of that function. Now there's always another possibility where the point where we have f dash x equal to 0, but when we do f double dash x equal to when we try to calculate, so let us say for f dash x equal to 0, we get the critical point as x1, and then we calculate the value of second derivative of x1, and we get this as 0 as well. So instead of getting a positive or a negative value, we are getting it as 0. So both the first and second derivatives at this particular point is 0. Now what we do? So these are called nothing but inflection points. So what is happening here is, so if you see the graph here, the value of the slope is greater than 0 for values which are less than this point, and the value of the slope is greater than 0 for the values even for greater than that point. So this is clearly neither a point of local maxima. So this is neither local maxima nor local minima. This is called an inflection point, and therefore this is not really very useful for any analysis which we normally do. Now although we have seen this, how do we calculate the local maxima and local minima, but why do we actually need this theory, and why would it be even used in something like machine learning algorithms and all? So in machine learning algorithms, what we normally encounter is something called an optimization function. This function is a function of various hyperparameters that are to be optimized to either maximize or minimize the function value. Now, for example, let us say we have a particular function and there's only one hyperparameter. So let us say we have a particular function fx equal to 5x square plus 6x minus 2. Now we need to find a value of the hyperparameter. So x is a hyperparameter such that the function value is maximized here. So whenever we encounter such a problem, what we do is we simply find the derivative of fx, we equate it to 0 to get the critical points x1 or x2. Then we find the second derivative. For the second derivative test, we put these points, and let us say if we are to maximize in this case, we will have to find the local maxima. So what we do, we put the points x1 and x2 in the second derivative, and if we get the second derivative as less than 0, we use that point. So use that point to get the local maxima, and this way we can maximize the optimization function. So once again, like, we don't have to worry about the optimization function right away in this particular session, but I was just giving an example of where this particular technique could be used in future when we are studying those different machine learning algorithms. Okay, so now till now we have been looking at functions in one variable, which was x. So x was one variable and we were looking at a function fx. But what if we have function in multiple variables? Now let us say we have a function in two variables x and y, such that it is defined as xy plus x upon y. Now let us say we have to find the derivative of f with respect to x. So we have to find d of fx y with respect to dx. Now how do we do that? So there is something called partial derivatives. What we do, we simply keep other variables as constant. And find the derivative. So for example, in this case, by the way, this partial derivative is denoted by this particular sign. So delta becomes, instead of df upon dx, this becomes delta f upon delta x, and this is computed as, so we simply assume that y is constant in this case. So del f upon del x will become y plus 1 upon y. So we are finding the derivative with respect to x, and since y is a constant here, we can simply bring x outside, and this becomes y plus 1 upon y, and this is a constant, so this can be brought outside the derivative operator, and the derivative of x is 1. Therefore we are left with y plus 1 by y as the required partial derivative. Now what if we have to find the partial derivative with respect to y? So del f upon del y, this time we keep y as constant, so we are left with x plus, x is a constant, so we bring it out. 1 upon y derivative is minus 1 upon y square, because y minus 1 becomes minus 1 into 1 upon y square. So therefore we are left with x minus x upon y square as the required partial derivative. So this is how we can compute the partial derivatives of functions in multiple variables. Obviously, this can be also computed for functions in more number of variables. So for example, we can have a function in xyz. So this is, let us say, x square plus y square plus z square plus 3xyz. Now del f upon del x becomes 2x. Now the derivative of y square would be 0, because y and z are constant. So we have 0, 0, and then plus 3yz. So we are left with 2x plus 3yz. Similarly, we can easily find the other derivatives using the same method. So we'll have 2y plus 3xz and 2z plus 3xy. So this is how we compute the partial derivatives of functions, which functions in multiple variables. Now what we are going to do, we have already looked at functions in multiple variables and how we can find the partial derivatives of those functions with respect to any one of those variables. So we simply keep the other variables as constant and find the derivative like we earlier used to. Now a continuation to this could be something called a mixed partial derivative. So now let us say we take a function f x y So this is a function in actually 4 variables here. So this is not just xy but xy, z and t. So all the 4 are variables in this case, and we need to now, let us say, what we do, instead of finding the single partial derivative, we try to find the double partial derivative, and that too with respect to different variables. So let us say we first find the partial derivative with respect to z. So del f upon del z. So this is xy minus z square t, because the partial derivative of 1 by z is minus 1 upon z square. Then plus y upon 2 root z, because partial derivative of root z is partial derivative of 1 by 2 z raised to power 1 by 2, which using power law becomes z raised to power minus 1 by 2, which is 1 upon 2 root z. So once we are done, and the partial derivative of this particular term would be 0 with respect to z, therefore we don't have to account for that. Now what we do, we further partial differentiate this particular function with respect to another variable. So let us say we do it with respect to x now. So we have del f upon del x del z, but since we are doing it twice, this is del square f, and we are left with, so now we are doing it with respect to x, therefore rest of the variables becomes constant in this case. Even z becomes now constant again. So we are left with minus y upon z square t. So this is how we can calculate the mixed partial derivatives. That is, we first calculated the derivative with respect to one particular variable, and then we find the partial derivative of the answer which we got from the first one with respect to some other variable. Similarly, we can have del square f upon del y del z. So in this case we are doing it with respect to y, therefore rest of them will become constant, and we are left with minus x upon z square t plus 1 upon 2 root z. Now similarly we can also do it with respect to, let's say, t, and so 1 upon t derivative is minus 1 upon t square, so minus minus becomes plus, and we are left with xy upon z square t square. And finally we can repeat the derivative with respect to z itself. So this becomes del square f del z square, which is nothing but, so minus 1 upon z square derivative is minus 2 upon z cube, because z raised to power minus 2, so this becomes minus 2 z raised to power minus 3, which is minus 2 upon z cube. Therefore we are left with 2xy upon z cube t plus, now for 1 upon root z, this is z raised to power minus 1 by 2, therefore the derivative would be minus 1 by 2 z raised to power minus 3 by 2. So we are left with, so this becomes minus y upon 4 z raised to power 3 by 2. So this is how we can calculate the mixed partial derivatives with respect to multiple variables and in any order we want to calculate. So this is about the mixed partial derivatives. Now why this is important is, oftentimes in the optimization functions, which I just showed even in the previous in the previous topic which we were looking at, where we were looking at even single functions. So we were trying to optimize a function in one variable here, but oftentimes there are multiple hyperparameters involved in a particular machine learning algorithm, and we need to maximize the function. So what we need to find the values of the each hyperparameter to maximize that function. And how we do that is, we simply equate the partial derivative with respect to each hyperparameter equal to 0. So let us say we have a function in 2 variables. So what we do to maximize it, we do del f upon del x as 0 and del f upon del y equal to 0. And now these two, there are 2 equations which we get. We solve 2 equations to get the hyperparameter value. So this is an application of how the partial derivatives could be used. Now, the final thing for this particular session is something called the chain rule for partial derivatives. So if you remember, there was a chain rule which we studied during the differential calculus as well, where we were using the chain rule to calculate the derivative of a function which was a function of another function. So what we were doing was we were just substituting that function, the internal function, with a new function and trying to use the chain rule to get to the final derivative. So here also, now let us say we have a function f x y. So basically it's a function in two variables x and y, and x itself and y itself, both of these are functions as well, and x is a function of two variables r and s, while y is also a function of same two variables. Now let us say we are asked to calculate the partial derivative of f with respect to r. Instead of x and y, we are told to find the partial derivative of f with respect to r. Now since both x and y are functions of r and s, the answer would not be 0. Even though r is not directly coming in fxy, it is a function of x and y, but both x and y could be written in the form of r and s. Therefore, del f upon del r would not be 0. So what we do, we use the chain rule here. So we differentiate f by x itself, but then we need to differentiate x with respect to r. So if you see, the del x will cancel out here and we'll be still left with del f upon del r. But then there is another variable in f, that is y. Therefore, we need to account for that as well. We write del f upon del y and into del f upon del r. So this is how we use the chain rule to calculate the partial derivatives when the function is a function of other functions. So for example, let us say, now again del f upon del s would be calculated in a similar way. Del f upon del x and del x upon del s plus del f upon del y and del y upon del s. So this is how we can calculate the partial derivatives. So let us look at an example now for this particular problem. So we have fxy. Let us say this is equal to x cube plus y cube. Then we know that xrs is a function of r and s. So let this be 3r plus 2s. So let it be a linear one. While for rs, y, let it be a quadratic one. So r square minus, let us say 3s. Now here we know that del f upon del x is equal to 3x square, because y would be a constant. Del f upon del y equal to 3y square, because x square will be a constant. And then del x upon del r is 3, while del x upon del s is 2. And del y upon del r is 2r, while del y upon del s is minus 3. Therefore, del f upon del r is del f upon del x, which is 3x square, del x upon del r, which is 3, plus del f upon del y, which is 3y square, and del y upon del r, which is 2r. So we are left with 9x square plus 6ry square. So this is how we can calculate the value of the mixed partial derivatives, or we can use the chain rule to find this kind of derivatives here. Similarly, one can calculate del f upon del s in a very similar manner. So this is it from this particular session. So we mainly looked at initially we looked at one example of finding the local minima and maxima. Then we looked at what are inflection points. So they are neither local maxima nor local minima, because the second derivative value itself is equal to 0, since there is no change in slope before and after the inflection points. Then we looked at an practical application, where would a local maxima and minima problem could be used in. So it is used in those optimization functions in machine learning algorithms. So one need not worry about that right now, but was just mentioning how they are used in machine learning algorithms. Then we introduced partial derivatives, how we can find the derivative of a function in multiple variables with respect to any one of those two variables or more than two variables. We can find the partial derivative by assuming other variables as constant and simply differentiating it with the main variable. Then we looked at mixed partial derivatives, where what we were doing were, instead of doing a partial derivative with respect to one variable, we can do it with respect to multiple variables in a like a sequential manner. So first we do the partial derivative with respect to z here, and then with respect to x. We could have done it with respect to x first and then with respect to z. So all kind of possibilities are there, and these are the notations which are used to denote these mixed partial derivatives. And then finally, we looked at how we can find the partial derivatives when the function is a function of other variables. And here we use the chain rule for partial derivatives to get the required final partial derivatives. And we also looked at this particular example to show this particular theory. So this is it from this session. So in the next one, we would be looking at a machine learning algorithm. So we'll be looking at ordinary least square regression, and we'll be actually applying whatever we have learned in differential calculus in terms of local maxima, local minima, as well as partial derivatives, how we can get an equation of a best fit line for a regression problem.